Q7296. If a pilot suspects that the engine, with a fixed-pitch propeller, is detonating during climb-out after takeoff, the initial corrective action to take would be to A. Lean the mixture. B. Lower the nose slightly to increase airspeed. C. Apply carburetor heat. The correct answer is B. Detonation during climb-out. Detonation is an abnormal combustion phenomenon that can occur in an aircraft engine. If the pilot suspects that detonation is happening during climb-out after takeoff, it means that the engine is experiencing uncontrolled combustion, which can lead to knocking, pinging sounds, and potential engine damage. Lowering the nose. Lowering the nose slightly to increase airspeed. This action is taken to address the conditions that contribute to detonation and to improve engine performance. Increasing airspeed. Lowering the nose of the aircraft results in a downward pitch, which increases the aircraft's angle of attack and airspeed. Increasing airspeed helps in multiple ways. A. Cooling effect. Higher airspeed increases the flow of air over the engine and its components, providing better cooling. The increased airflow helps dissipate heat generated during combustion, reducing the likelihood of detonation. B. Improved cylinder filling. A higher airspeed improves the ram air effect, leading to increased pressure and density of the intake air. This results in a better air-fuel mixture entering the cylinders, which can help prevent detonation. C. Increased combustion efficiency. With increased airspeed, the engine is operating at a higher power setting, which can result in improved combustion efficiency. This can reduce the likelihood of detonation by promoting a more controlled and even burning of the fuel mixture. Additional corrective actions. It's important to note that lowering the nose to increase airspeed is the initial corrective action. If detonation persists or worsens, the pilot may need to take further actions such as adjusting the mixture to a slightly richer setting, reducing power, or seeking assistance from air traffic control or the appropriate maintenance personnel. Therefore, if a pilot suspects that the engine with a fixed-pitch propeller is detonating during climb-out after takeoff, the initial corrective action to take is to lower the nose slightly to increase airspeed. Increasing airspeed helps improve cooling, cylinder filling, and combustion efficiency, all of which can help address the conditions leading to detonation and ensure safe engine operation. 7298. Detonation can be caused by A. A short ground operation. B. A rich mixture. C. Using a lower grade of fuel than recommended. The correct answer is C. Detonation. Detonation is an abnormal combustion phenomenon that occurs when the air-fuel mixture in an engine ignites almost simultaneously, resulting in a rapid and uncontrolled burning. It can lead to knocking or pinging sounds and potential engine damage. Lower grade of fuel. Detonation can be caused by using a lower grade of fuel than recommended by the engine manufacturer. The grade of fuel refers to its octane rating, which indicates its resistance to detonation. Lower-grade fuels typically have lower octane ratings and may not provide sufficient resistance to detonation. Octane rating. The octane rating is a measure of a fuel's ability to resist detonation under high pressure and high temperature conditions. Engines are designed to operate with fuels of a specific octane rating, and using a fuel with a lower octane rating than recommended increases the risk of detonation. Detonation causes. Using a lower grade of fuel can contribute to detonation in the following ways. A. Pre-ignition. Lower-grade fuels may have a lower resistance to pre-ignition, where the air-fuel mixture ignites prematurely before the spark plug fires. This can lead to multiple flame fronts within the combustion chamber, causing uncontrolled and rapid burning, which is characteristic of detonation. B. Higher cylinder temperatures. Lower-grade fuels may have a lower heat-absorbing capacity compared to higher-grade fuels. This can result in higher cylinder temperatures, which can increase the likelihood of detonation. C. Poor combustion control. Lower-grade fuels may have a lower ability to control the combustion process, leading to uneven burning and potentially contributing to detonation. Consequences of detonation. Detonation can cause severe stress and damage to engine components. The rapid and uncontrolled pressure rise puts excessive strain on pistons, connecting rods, cylinder heads, and other engine parts. Prolonged detonation can result in piston damage, bent valves, cracked cylinder heads, and other critical engine failures. Therefore, using a lower grade of fuel than recommended by the engine manufacturer can increase the risk of detonation. Lower grade fuels may have lower resistance to pre-ignition, result in higher cylinder temperatures, and offer poorer combustion control, all of which can contribute to detonation. It is crucial to use the fuel grade specified by the engine manufacturer to ensure safe and efficient engine operation. 7301. Detonation occurs in a reciprocating aircraft engine when a. There is an explosive increase of fuel caused by too rich a fuel/air mixture. b. The spark plugs receive an electrical jolt caused by a short in the wiring. c. The unburned fuel/air charge in the cylinders is subjected to instantaneous combustion. The correct answer is C. Detonation. Detonation is an abnormal combustion phenomenon that occurs in an engine when the fuel/air mixture ignites almost simultaneously and leads to a rapid and uncontrolled burning. It is characterized by knocking or pinging sounds and can cause engine damage if not addressed. Unburned fuel/air charge. Detonation occurs when the unburned fuel/air charge in the cylinders is subjected to instantaneous combustion. During the normal combustion process, the fuel/air mixture should burn progressively and evenly, generating power. However, in the case of detonation, the unburned charge ignites in an uncontrolled manner, leading to a rapid pressure rise and the characteristic knocking sound. Instantaneous combustion. Detonation occurs when the unburned fuel/air charge in the cylinders undergoes instantaneous combustion. Instead of a controlled, gradual burn, the fuel/air mixture ignites almost simultaneously, resulting in a rapid release of energy and pressure within the combustion chamber. Factors contributing to detonation. Several factors can contribute to the occurrence of detonation. A. High cylinder temperatures. Elevated cylinder temperatures, often caused by factors such as advanced ignition timing or lean fuel mixtures, can increase the likelihood of detonation. When the temperature is excessively high, the unburned charge can ignite rapidly and lead to detonation. B. High compression ratios. Engines with high compression ratios are more prone to detonation. Higher compression ratios create increased cylinder pressures, which can cause the unburned charge to ignite instantaneously and result in detonation. C. Lean fuel mixture. A lean fuel/air mixture, where the ratio of air to fuel is higher than optimal, can contribute to detonation. Lean mixtures burn faster and can lead to uncontrolled ignition and detonation. Consequences of detonation. Detonation puts significant stress on engine components. The rapid and uncontrolled pressure rise places excessive strain on pistons, connecting rods, cylinder heads, and other parts. Prolonged detonation can lead to piston damage, bent valves, cracked cylinder heads, and other serious engine failures. Therefore, in a reciprocating aircraft engine, detonation occurs when the unburned fuel/air charge in the cylinders is subjected to instantaneous combustion. Factors such as high cylinder temperatures, high compression ratios, and lean fuel mixtures can contribute to detonation. It is crucial to operate the engine within recommended parameters and address any issues that may lead to detonation to ensure safe and reliable engine performance. 6664. Which statement is true regarding propeller efficiency? Propeller efficiency is the A. Ratio of thrust horsepower to brake horsepower. B. Actual distance of propeller advances in 1 revolution. C. Difference between the geometric pitch of the propeller and its effective pitch. The correct answer is A. Propeller efficiency. Propeller efficiency refers to how effectively a propeller converts engine power into thrust. It is an important factor in determining the performance and fuel efficiency of an aircraft. Thrust horsepower. Thrust horsepower is the power required to produce the thrust generated by the propeller. It is the actual power output that contributes to the forward motion of the aircraft. Brake horsepower. Brake horsepower is the power measured at the engine's crankshaft or output shaft. It represents the total power output of the engine without considering any power losses. Ratio of thrust horsepower to brake horsepower. Propeller efficiency is the ratio of thrust horsepower to brake horsepower. This ratio provides a measure of how effectively the engine's power is being used to produce thrust. Significance of the ratio. The ratio of thrust horsepower to brake horsepower indicates the efficiency of the propeller in converting the engine's power into useful thrust. A higher ratio signifies a more efficient propeller, as a greater proportion of the engine's power is being utilized to generate thrust rather than being lost to other factors such as friction or drag. Factors affecting propeller efficiency. Several factors influence propeller efficiency, including the design of the propeller, its pitch, the engine's power output, and operating conditions. Propeller efficiency can be affected by variables such as altitude, air density, and airspeed. Importance of propeller efficiency. Propeller efficiency plays a crucial role in an aircraft's performance, including its climb rate, cruise speed, range, and fuel consumption. Higher propeller efficiency results in improved overall performance and fuel economy. Therefore, propeller efficiency is correctly defined as the ratio of thrust horsepower to brake horsepower. This ratio provides a measure of how effectively the propeller converts engine power into useful thrust, indicating the propeller's efficiency in utilizing the available power for forward motion. 6590. Blade angle of a propeller is defined as the angle between the A. Angle of attack and chord line. B. Chord line and plane of rotation. C. Angle of attack and line of thrust. The correct answer is B. Blade angle. The blade angle of a propeller refers to the angle at which the propeller blades are oriented in relation to the plane of rotation. Chord line. The chord line of a propeller blade is a straight line connecting the leading edge to the trailing edge of the blade. It represents the reference line along which the aerodynamic forces act. Plane of rotation. The plane of rotation refers to the plane in which the propeller rotates as it spins around its axis. It is perpendicular to the axis of rotation. Definition of blade angle. Blade angle of a propeller is the angle between the chord line and the plane of rotation. This means that the blade angle is measured by considering the orientation of the chord line with respect to the plane in which the propeller rotates. Importance of blade angle. The blade angle plays a significant role in determining the performance characteristics of the propeller. It affects the amount of thrust generated, the efficiency of the propeller, and its ability to produce forward motion. Adjustable blade angle. In some propeller designs, the blade angle can be adjusted. This allows for optimizing the propeller's performance under different flight conditions, such as during takeoff, climb, cruise, or descent. Variations in blade angle. The blade angle can vary along the length of the propeller blade. Near the hub, where the blade is wider, the angle may be more significant, while toward the blade tip, the angle may be reduced. Therefore, the blade angle of a propeller is correctly defined as the angle between the chord line and the plane of rotation. This angle determines the orientation of the propeller blades and plays a crucial role in the propeller's performance and ability to generate thrust.